Welcome. In this session, we will look at the concept of a differential. We will make use of this in our discussions of integrals, our next major topic. Differentials are an alternate way of looking at the approximation properties of derivatives. We talked about this in a rather limited way in the beginning of chapter 11. If f is a differentiable function, then f of x minus f of c is approximately f prime of c times x minus c. A different way of thinking about this is that if I have a function f, I change x by a small amount, the function changes by a certain amount, which we denote by delta f, as we did when talking about rates of change. And df is an approximation to that. It's a linear approximation. The formal definition of the differential is that it's derivative times dx. You should think of d as indicating the change, and df is not the actual change but an approximation to the change given by the derivative. So we think of df as depending on two variables, x and dx. So you start at x and then change the value of the variable by dx. So you go from x to x plus dx. Then df is the rise in the tangent. So for a straight line, rise is slope times the run, and that's what f prime of x dx is. And this is an approximation to the actual rise in the function because the tangent is close to the curve, at least if you don't move too far away from the point of tangency. The main use of differentials nowadays is in theoretical work. It can be used to approximate values of the function when you change the variable by a small amount. So if f is a differentiable function, then f of x plus dx is, by definition, f of x plus the change in f. We can approximate the change in f by df, and df is f prime of x dx, which means that f of x plus dx can be approximated by f of x plus f prime of x dx. We will look at a couple of illustrations of this in the next session. This will motivate our definition of the Riemann integral in section 6.